Is that positive 16 or negative 16?
Oh, sorry, it's supposed to be minus 16, yeah. Yeah, minus 16. That's right. Okay, and you can do the following. Okay, so I also want to mention one big connection between what we taught here with the contour map. So contour map is the map that consists of the level curves, right? And also we proved this very interesting result from last lecture, which is relating the contour map, the level sets with the gradient vectors. What's the property we proved? Still remember? The gradient vector. What is the property we proved? That relates. So the gradient vector always orthogonal to the level curves, right? It's always orthogonal to the level curves. More strictly speaking, it's the tangent lines. Right? Level curve is a curve. We're talking about orthogonality, so it has to be a vector with another straight line or another vector. So the gradient is always orthogonal to the tangent vector, the tangent line or the tangent vector of the level curve. So I want to give you one example to really see this following fact. So we have a function f(x, y) is equal to 14 minus 2x squared minus 5y squared. So I want to look at this point, p minus 1, minus 1, and 8. So minus 1, z is exactly equal to 8. So this point is on the surface, on the graph of this function. I want to quickly quiz you again. If I want to graph this function, z is equal to 14 minus 2x squared minus 4y squared, which kind of surface is it?
It's a line.
So z is equal to this guy. I have squares. It's definitely not a plane anymore. All right. All the terms are square or lower order terms. This is definitely a quadratic surface. This is going to be a elliptic parabolic opening downwards with axis with z-axis. Right? So the reason you can see that is if you fix one z, let's be careful. How do we immediately derive all the things? Remember that. We compute the intercepts, we also compute the traces, right? Getting the traces is extremely useful, not only when we want to graph the exact formula and the exact surface. It is also quite important for you to tell which kind it is. If you fix a z, you're getting 2x squared minus 4z squared is equal to number, and then you can simplify it into an elliptic. All right? Are you with me? So I will give you an example where you can actually see it is an elliptic. If I make x equal to 0, you're getting z is equal to 14 minus 4y squared. This is a parabola. All right? This is a parabola actually opening on the yz plane downwards. All right? If I make y equal 0, I'm getting z is equal to 14 minus 2x squared. It's still a parabola. All right? On the xz plane, it's opening into the z-axis. Right? Opening to the negative direction of the z-axis. So this is opening to the negative direction of the z-axis on the yz plane as well. So you have one ellipse and then two parabolas opening downwards. This is definitely an elliptic parabola. All right? So the graph roughly looks like this thing. Okay? Okay, so we're about to get our first midterm, so you start, it's not a good time to start forgetting stuff, right? So this is the equation of the function I have. And I want to look at the level at z is equal to 8. Right, this is essentially the level curve that will contain this point. All right? You guys seem to be confused.
No,
No?
you're
Okay?
the only thing we know.
Okay. So if I want to draw the level curve at this point, z value is exactly telling you what level it is, all right? So I'm just drawing the level at z equals 8, and this level curve will exactly contain this point, right? And also it can verify what I was talking about in order to get this ellipsis. So this is going to be 8 is equal to 14 minus 2x squared minus 4y squared. So you can simplify this whole thing to get a, let's see, 2x squared plus 4y squared is equal to 6. So in order to see exactly what this is x squared divided by 3 plus y squared divided by 3 divided by 2 is equal to 1. All right? Then you can be convinced. At this level, z equals 8, I am getting an ellipsis with x is square root of 3, y is square root of 3 divided by 2. Right? So this is indeed an ellipsis. So the level curve is on xy plane, so I will be able to get a, so x is slightly longer. This is 1. So z is equal to 8. This is minus square root of 3, this is square root of 3, this is square root of 3 halves, this is minus square root of 3 halves. Okay, so this is the level curve. And my point is at a minus 1, so this is going to be where the point is. Okay, so this is p minus 1, and the value at this point is exactly equal to 8. So there are two things I can compute. Okay, in order to verify these two are orthogonal, I can immediately get a gradient of f at this point. All right? Which is just a matter of computing the partial derivatives. Gradient is a vector consisting of all the partial derivatives in a symmetric form. So George, work with me again. So if I'm going to compute the gradient vector here, what I'm getting? This is the function. So it's a minus 4x minus
negative
81. So if I want to evaluate at the point minus 1, this guy is equal to 4 and 8. Very good. So this is the gradient vector. Okay? So in order to verify these two vectors are orthogonal, I'm getting already one of them. I needed to find the tangent line of the level curve. Okay? So tangent line of the level curve is essentially talking about the tangent line of the curve defined by this equation. Am I right? Yes, this is the equation defining the level curve. And I want to find the tangent line. The tangent line of this curve, which is essentially a one-dimensional object, is just a matter of taking regular derivative. All right? The tangent line is just a matter of taking regular derivative of y with respect to x. All right? And we have done this before. If I want to find the derivative dy over dx for this equation, I can use the implicit differentiation. Right? I can use the implicit differentiation. Or we can even go to the very origin of implicit differentiation, which is just a matter of taking derivatives on both sides of the equation. Right? So we can do that even more directly. So here is what I'm going to do. I'm looking at this equation in the box. I'm taking derivative on both sides with respect to x. Okay? With respect to x, y is a dependent variable, depending on what? X. So when I take derivative in this term, I have to worry about derivative with respect to x, which requires the chain rule. Right? So I take the derivative on both sides. I'm getting 0 is equal to
0
minus 4x minus 8y and y prime. All right? So that's the taking derivative on both sides. So what I did here is dx on both sides. So as I said, doing this is equivalent of using implicit differentiation theorem. Okay, it's up to you. You can either take the derivative directly, or you can name a capital F x y and do the partial derivative with respect to x and with respect to y, and use the implicit function theorem. And the key thing for implicit differentiation theorem is there is a minus sign in the formula. Okay, keep yourself reminded. So if you have a function f(x,y) equals 0, so dy over dx is going to be equal to minus f sub x and f sub y. So you have a minus sign over there. So simplify this whole thing, I'm getting a y prime is equal to minus x divided by 2y. X is equal to minus 1, y is equal to minus 1, so I'm getting a minus 1/2. Okay? So y prime is equal to minus 1/2. This is talking about the slope of the tangent line at this point. All right? This is talking about slope of the tangent line at this point. And I need to design a vector which is pointing to the direction of this straight line. Basically, you can design two vectors, right? You can design two vectors on the same direction as this straight line, right? So one is in this direction, the other one is the other direction. And then I have a gradient vector so I can check whether these two are indeed orthogonal. Yes? Okay? So the question arises here is, if I know the slope of the tangent line, how do I find a vector which is parallel to this straight line? We actually talked about this in last Wednesday. And so if I have a slope of a tangent line, and I want to talk about the vector which is in the same direction of a straight line, you need to interpret the slope in a more direct way. What do we mean by slope? If the slope of a straight line is m, it's essentially talking about if you increase x by 1, y will be increased by m. Am I right? So if the slope of a tangent line is equal to m, it is talking about if you increase x by 1, y will be increased by m. If m is positive, it will be decreased by absolute value of m if it is negative. All right? So that's basically what the slope of a tangent line or slope of any straight line is about. So if I know there is a slope of minus 1/2, I can easily design a vector with x component 1, y component of whatever slope it has. Do you agree with me? Okay? So I can find a vector in the direction of the tangent line as 1 and minus 1/2. So it's pretty easy. As long as you have the slope, you will get one vector, and in fact, there's another vector which is the opposite direction, so minus 1 and 1/2. Both of these two vectors are parallel to the straight line you're getting right here. Okay, you can use one of them or the other one of them. Okay, you can also normalize these vectors if you want. Okay, you can also normalize these vectors if you want. For instance, here, normalization is going to be 2 square root of 5 divided by 5 and minus square root of 5 divided by 5. And after normalization, this is going to be minus 2 square root of 5 divided by 5 and plus square root of 5 divided by 5. So these are the normalized vectors which are in the same direction of the tangent line at this point. Okay? In fact, let's see. This is the vector right here. Okay? X positive, y negative. So it's pointing in this direction. This vector x negative, y positive is going to be pointing to the opposite direction right here. So there are two vectors which are tangent to the curve right here. Now again, this is essentially why we recall a lot of the calculus computation in the very beginning. If I want to check this vector and this vector is orthogonal, what do we do?
Dot product equals.
We do the dot product, right? So to check two vectors are orthogonal, you do the dot product. If you want to check two vectors are parallel, you need to do the cross product. So 4 and 8 times 1 and minus 1/2, you can easily check they are indeed orthogonal. Am I right? 4 minus 4, you're getting a 0. So at this point, the gradient will be going this way. Okay, so this is going to be the gradient. Gradient of x. Gradient is 4, 8, x positive, y positive has to be pointing in this way. Okay, and you have two tangent vectors at this point. So these vectors are all orthogonal to the tangent vector. I'm sorry, these are all orthogonal to the gradient vector over here. Okay, so this is how you compute all the things related to contour map. Questions? Yep.
Where did you get the 2 root 5 over 5 and the root
Oh,
5?
these are just the normalization. So this is the normalization. Which is literally to make this vector of unilength. That's what I did. Okay? You can compute the length of this thing and simplify whatever you have. Here is a quick trick to compute the normalization vector, the unit vector in the same direction. Okay? I want to find the unit vector which is in the same direction of this vector. The only thing I care is the ratio between these two components. Okay, so the ratio between these two components is 2. And I want to make sure my vector is of unit length. This is the only choice. Okay, it is of unit length, and the ratio between the x and y components is actually -2. Okay, right? You think about that. If you want to derive a unit vector in a direction in R2, the only thing that matters is the x and y ratio. Right? So that will tell you what direction it is. Okay, so digest a bit about what we have talking about for the last 1.5 hours. So gradient vector is a vector to begin from. Directional vector is also a vector, and then given a directional vector, I'll be able to compute the directional derivative with respect to that direction. And that is going to be a rate of change, and that's a number. If we change different directions, we're getting different directional derivatives. Some of them are large, some of them are small. We can find one particular direction, U max, where the directional derivative is maximum. We can also find the opposite direction, where the directional derivative is minimum. So these are the keywords we talk about for the whole gradient discussion. So think about it. How many objects you're dealing with here? 3 objects. What are the relations between them? Okay, and this is the very first application of partial derivatives. I'm going to say it again. Taking partial derivatives is extremely easy, and it is exactly the same thing as single variable calculus. You're computing the directional derivatives. You're essentially taking the derivative with respect to one single variable, and that's it, right? But we want to use these partial derivatives into calculus, and this gradient vector is the very first application. Especially, you can see these partial derivatives, when combined in a symmetric form, they will be pretty powerful. Right? So the gradient vector is not a partial derivative. It's a vector